Heating and cooling agitated liquid batches, isothermal. Course contents. As I stated previously, there are many industrial instances whereby the desirable estimate time required with the heat or cool volume of liquid is being agitated in a tank or reactor vessel. Two common industrial processes, equipment configuration, are continue found and represented in the figures 1 and 2. All figures located at the end of the course of the outline text. Figure 1 represents the augmented heat batch level of the being by a medium which is passed through a jacket surrounded with a section of the vessel containing the liquid saturated steam, indicated with the example of the heating method medium. Figure 2 represents the batch liquid being cooled with a submerged coil mounted inside of the tank with liquid volume. A Freon-based refrigerant R22 is indicated with the example of the cooling medium. In the case of the batch, energy for the energy transfer with the heating medium of the cooler liquid batch, see figure 3, with the temperature for the medium remain constant, energy must contain its phase change of the saturated vapor to the saturated liquid economies of the batch. In cooling figure 4, energy is transferred from the hot batch of the cooling medium for a temperature of the medium to the remain constant for the energy must originate with the phase change of the saturated liquid to saturated vapor. Assumption 6. The origin and application equation start with a differential heating balance between click off of the medium and liquid in order to account for the heat flow, the high temperature for the low temperature for the course of the evolve of the equation, each of the heating of the cooling applications. It will also be assumed that there is no liquid being vaporized or crystallized during the heating of the cooling of the event. Assumption 4. Definition: isothermal equals fluid remains constant temperature. Simplifying assumptions were used in developing the heating and cooling application equipment equations. They assume arise here. Specific heat of the batch liquid, the CP batch constant will be estimated the average of the initial final temperature for the overall heat transfer. The coefficient U of the U jacket or coil is constant over the entire heat transfer surface area A jacket coil. The agitation produced the uniform fluid temperature throughout the batch liquid mass. No phase change of the curve in the batch liquids. 5. Heating and cooling media have a constant inlet temperature flow rate. 6. The heating and the cooling media undergo isothermal heating changes. Phase changes of the heat loss for the environmental are negligible. Heat is heat agitated liquid batch isothermal medium mass for liquid mass liquid batch. M batch is at a specific heat of CP batch. Heat energy liquefied. Q is defined as heat energy of the fluid is equal to the mass of the batch liquid being heated or cooled, expressed in pounds, times the heat capacity of the liquid batch expressed in the BTUs in pounds per Fahrenheit, times the T batch with the temperature of the batch liquid at any time expressed in degrees of Fahrenheit is equal to the heat transfer in the BTU per hour. Q. Specific heat of the batch will be assumed with the constant of the specific heat U for the application equation with the estimated with the average initial and final batch temperatures. Assumption 1 per unit time. O is change of the heat with the energy liquid respect with the changing temperature given with the dQ is equal to the MDO, which is the unit in time, is equal to the M batch plus C batch plus D batch divided by the time calculated. The other equation of the heated agitated liquid batch isothermal medial, and the time equal the time is calculated heat or coil batch from initial final temperature expressed as in hours. At any time given the heat transfer, the transfer coefficient U, the heat was relieved for the medium transfer of the batch liquid through the vessel wall as equal to Q, assuming the negligible heat loss of the environment. Assumption of the S7 will also make the simplifying assumption overall heat transfer coefficient constant overall and time transfer area. Assumption 2, the heat transfer rate is defined as Q, negligible heat loss let's see. Q, you're assuming negligible heat loss is equal to the heat released by the medium and transfer of the batch like through the vessel wall is equal to A jacket U times A times T. The medium is the fluid supply with the heating of the cooling energy vessel jacket of the tank. A jacket of the jacket transfer utilized with the heating of the cooling medium with special square feet available to transfer surface of the transfer heat for batch liquid. A coil heated tube of the transfer area utilized with heating cooling medium expressed in square feet and available transfer for the transfer heat to and from batch liquid. U jacket overall heat transfer coefficient Using conjunction with the jacket heat transfer area expressed in BTU hours square foot in Fahrenheit. And U coil overall heat transfer coefficient U with the conjunction with the coil heat transfer area with expressed in BTUs hours square foot times Fahrenheit. It should be noted for the calculation which are jacketed vessels heating the appropriate terms U and the jacket and A U jacket and A jacket would be substituted with above the equation. Likewise, with the calculation which are intended to represent vessels submerged in heat coiling within terms of the U coil and A coil should be U the temperature deriving forces defined as the temperature T heat is equal to T heat to minus T batch. Where you get T heat with the isothermal temperature of the heating medium expressed in degrees Fahrenheit times the batch temperature minus the temperature of the batch, equating in 2 yields of the M batch, C batch, D T batch, and the DO is equal to U times A times T. Substitute equations Q and equations 4 and 5. M batch Q times T batch divided by DU is equal to U times A times T heat times T batch 6. And regarding similar differential terms of the growth, grouping together with the constant yield of the DT batch heat T minus T batch is equal to U times A minus B, U times A divided by B M batch times B C batch times DO has been integrated between times of the O. Alright, DT batch is divided by T heat times T minus T batch is equal to U times A divided by M batch times C batch times DO. Alright, the O at the start of the cycle will correspond with the T initial, the initial Z final, the finish cycle will correspond with the T final temperature of the batch liquid expressed in degrees Fahrenheit. T initial of the initial temperature of the batch liquid expressed in degrees Fahrenheit. As a result, the Ln is equal to Ln is the T heat minus Tn times T heat minus T final is times T Ln is equal to UA and times the U times A times hours divided by M batch times C batch. Arranging time variable use the following equation: O hours equals to Ln T times T heat times Nn T times T final times M batch times C batch divided by U times A. Cooligated liquid batches isothermal media for mass liquid batch, specific heat C batch. Each energy field will define as Q is equal to M batch times CP batch times T batch. Per unit change in heat energy liquid respect the changing temperature is given by any time given the heat transfer area and the transfer coefficient U heat with the transferred batch liquid through the vessel wall is defined as Q times A. Q is equal to U times A times T. Should be the calculation which restricted vessels heating appropriate terms. The U jacket, A jacket should be substituted in the above equation. Likewise, calculations which intend to represent visual and submerged heating coil with the terms representing the U coil, A coil would be used. Temperature driving force is defined as T. Temperature driving force is equal to T batch minus T coil, T batch minus T cool. T cool is the isothermal temperature of the cooling medium expressed in degrees Fahrenheit. Equation 1213, M batch times Q batch times D times T batch divided by DU is equal to U times A times temperature. Substituting equation 14 and 15. M batch times C batch times DT batch divided by DO, the hours is equal to UA times T batch times minus T cool. Rearranging similar differential terms, grouping them together in constant gives DT batch is equal to T batch minus T cool equal to U times A times divided by M batch times Q P batch times DO. Speaking integrated between the timelines, DT batch is equal divided by T batch minus tool batch is equal to F is times U times A divided by M batch C batch times D to the O. O is start of the cycle will correspond with the T initial. O final finish cycle correspond with the T final. As a result, the Ln T initial T coil time T final T coil UA hours M batch C batch. Regenerating time variable use following equations: 0 hours equals Ln to T initial times tool, T final times tool coil, M batch times Q divided by US. Alright, application equipment equation summary: U hours equals Ln times T heat times minus T initial divided by T heat minus T time T final times M batch times C patch divided by U times U times A. Isothermal cooling. Aggregated OH ln T initial T minus T cooling 2 heat T final times cooling. Mem batch C batch QE UA. Alright, physical property data. Water liquid density 110 degrees Fahrenheit, 8.27 liquid gallons pounds a gallon. Water liquid heated capacity 110 degrees Fahrenheit, 1 BTU at pounds per Fahrenheit. Steam saturation temperature 164.7 psi at 366 degrees Fahrenheit. R22 saturated temperature 34.7 psa at negative 5 degrees Fahrenheit. It is proposed to heat 5,000 gallons of the cold water aggregated jack vessel ventral atmosphere plant steams at 150 psi gauge used to the heating of the medium is given in the heat transfer over the jackets at 200 square foot. Then an overall heat transfer coefficient of 100 could be assumed. Calculate the time required with the water volume at 70 to 150 degrees Fahrenheit. Step 1, calculate the average temperature of the water. The T-batch average of the average temperature of the batch liquid expressed with the degree Fahrenheit. This would be used as the temperature of the determining of the physical property. The temperature average of it is equal to temperature initial less temperature final divided by 2. So that you have 70 plus 150 divided by 2, 110 degrees Fahrenheit. Your average temperature batch is 110 degrees Fahrenheit. Step 1 and 2, determine the density of the water over the average temperature from table 1, density 110 degrees Fahrenheit, 8.27 pounds per gallon. Calculate the mass water heated mass equals volume times density. So your mass batch at 5,000 times 8.27 things, you get 41,350 pounds. Determine the heat capacity of the water being heated from table 1 for the heat capacity of the QCP batch 41 BTU pounds per Fahrenheit. Step 1.5, determine the steam heating medium temperature at the plant supply pressure with the pressure's absolute units. Saturated steam heat temperature medium, the chemical property of the industrial chemical formula H2O with the normal boiling point with the water 212 degrees Fahrenheit. Its temperature pressure 14.7 psi or 0 psi gauge. When watering, the temperature of the pressure of both vapor and liquid saturated equilibrium with either each other. The typical steam tables you determine the saturation water temperature at various pressures. Pressure is equal to 150 10 plus 14.7 to 164.7 psa. For table 1, steam pressure for the T heat is 360 degrees Fahrenheit. Step 1.6, calculate the time required for the heat the mass of the water given the data obtained with the steps 1 through 1.5 above the evening application. So you'd have 39 minutes. It proposed to cool 5,000 gallons with the water aggregated vessel vented over the atmosphere, cooled with the internal coil with the coil inside with the coil done with the refrigerant R222 with the 20 psi gauge the medium. Given the heat transfer for the area of the coil with the 450 square foot with the average overall heat transfer for the coefficient 50 could be assumed. Calculate the time required to cool the water volume with 170 to 50 degrees Fahrenheit. Calculate the average time. If temperature average of the temperature initial plus temperature final divided by 2, which would be 170 plus 50 divided by 2, 110 degrees Fahrenheit. 110 degrees Fahrenheit for your average temperature of the water. Determine the density of the water over the average temperature of the table of the density of the 110 degrees at 0.27 pounds per gallon. Calculate the mass of the water to be heated. Mass equals volume times density. You'd have 1,000 times 8.27, which gives you 41,350 pounds and determine the heat capacity of being heated. Table 1 with the heat capacity of the 1 BTU per pound per Fahrenheit. Determine the cooling temperature for the plant supply with the pressure from the absolute unit. Freon 22, typical refrigerant commonly used under isothermal conditions. Commercial name refrigerant R22. R22 with the chemical formula CHClF2 with the normal boiling point with a compound of 41.4 degrees Fahrenheit. See reference of the saturation temperature vessel pressures. Pressure 20 plus 14.7 to give you 34.7 psia. From table, the coolant temperature of the 2 coolant is equal to negative degree Fahrenheit, 5 degrees Fahrenheit. Calculate the time required to cool the water given with the data obtained with the steps 2.1 through 2.5 above the using the application temperature to equation 2. You'd have 128 minutes for the time and the temperature initial to cool and temperature final to cool with the mass batch and Figure 1, agitated liquid in vessel under the heating jacket. Vessel data, volume 5,500 gallons, jacket heating transfer area 200 square foot, overall transfer coefficient 100 BTU hour per square foot Fahrenheit. Aggregated motor, liquid level, liquid volume 500 gallons, water 1.0 BTU pounds a foot, 8.3 pounds a gallon, 7 degrees Fahrenheit. Aggregated blades, vessel jacket, saturated steam 150 psi gauge 360 degrees Fahrenheit, condensated 150 psi gauge 360 degrees Fahrenheit, vessel jacket. Figure 2, agitated liquid in vessel, vessel data volume 5,500 gallons, coil heat transfer area 450 square foot, overall transfer coefficient 50 BTU hour, BTUs per hour over an hour square foot, and then temperature graded Fahrenheit. Aggregated motor R222 liquid 20 psi gauge down to 5 degrees Fahrenheit. Submerged coils. Liquid batch data 5,000 gallons. Fluid water level 1.0 BTU 8.3 pounds 7 degrees Fahrenheit. Aggregated blades R22 saturated 20 psi gauge -degree Fahrenheit and submerged coils. Figure 3 differential pressure represented the heat flow of the batch of liquid. Show the heat medium TH Q released to the medium different slice. Jacket wall area, A area jacket heat transfer coefficient, U jacket, Q absorbed liquid, batch liquid, T batch, Q batch, M batch. Temperature driving heat is T heat is greater than the T batch, T heat is minus T batch. The temperature driving force. Differential representation, heat flow, batch liquid cooling, shows the batch liquid, T batch, Q batch, CP patch, M batch. Q release liquid at different slices of the wall of the coil, A area coil, heat transfer coefficient, U coil, Q absorbed medium cooling, medium T coil is less than T batch, temperature driving force is equal to T batch minus T cool. Final exam, and that completes the reading of your heating and cooling aggregated liquid medium batch ISO 30 ml medium content.